Hi all, today we will derive one-dimensional heat transfer equation. To derive one-dimensional heat transfer equation, we need some empirical laws. Our law 1 is heat flows from higher to lower temperature. Heat flow through a solid is directly proportional to the cross-sectional area A and the temperature gradient. What is temperature gradient? Temperature gradient is nothing but the rate of change of temperature with respect to the distance, that is dou u by dou x. That means if Q is the heat flow through a solid, then it is equal to Q equal to Ka dou u by dou x, where K is the proportionality constant known as the thermal conductivity of the material. The quantity of heat required to produce a given temperature change is directly proportional to the mass of the body and the rate of change of temperature with respect to time. That is, Q is equal to Cm dou u by dou t, where C is the specific heat capacity of the material, M is the mass of the body, and dou u by dou t is obviously the rate of change of temperature with respect to time. To derive one-dimensional heat equation, we make the following assumptions. Choose a uniform bar of constant cross-sectional area, capital A, so that the mass per unit length is constant. So we are considering a uniform bar, conducting bar of constant cross-sectional area A, and mass per unit length is a constant. The sides of the bar is insulated so that the loss of heat from sides is negligibly small. We are considering a bar whose sides are insulated. We are insulating the sides in order to reduce the loss of heat from sides is negligible. That means heat flow through the rod is in such a way that heat flux is always perpendicular to the cross section. That means direction of the heat flow is along positive x-axis. Now consider the rod. Consider a point P which is at a distance x from the origin. We are placing the rod along x-axis such that 1 end is at the origin. Now P is at a distance x from the origin and Q is at a distance x plus delta x from the origin. So the length of your small portion is delta x, considerably small length. Now u of xt, we are going to find an equation satisfying u of xt, where u of xt is the temperature of the point x at some time t greater than 0. Q1 is the amount of heat energy flowing into the cross section P in time delta t. Then using our empirical law 2, Q1 is equal to minus Ka dou u by dou x at the point x, where K is the proportionality constant known as the thermal conductivity of the material and A is the cross section area of the material, and the negative sign indicates that heat flows in the direction of decreasing temperature. So we are assuming the heat flow starts from the origin and the heat flow is from left to right. So the negative sign simply indicates that the heat flow is in the direction of decreasing temperature. Again, Q2 is the amount of heat energy flowing into the cross section Q in time delta T. Then Q2 is equal to minus Ka dou U by dou X at the point X plus delta X, where K is the thermal conductivity of the material, and the negative sign again indicates that heat flows in the direction of decreasing temperature. So we have Q1 and Q2. The amount of heat retained by the element PQ in time delta T. So Q1 is the amount of heat flowing into the cross section, and Q2 is the amount of heat flowing out of the cross section, out of the small portion. So the amount of heat retained by the element PQ is nothing but the amount of heat flows into the small area PQ minus the amount of heat leaving the portion. So it is Q1 minus Q2. That is minus Ka dou U by dou X at the point X minus Ka dou U by dou X at the point X plus delta X. Taking Ka common and rewriting the equation, we get Ka into dou U by dou X at the point X plus delta X minus dou U by dou X at the point X. Call it as equation number 1. Now using law 3, the amount of heat required to raise the temperature of the element PQ is Q equal to Cm dou U by dou T, where C is our specific heat capacity, M is the mass. Since A is the area of cross section and if rho is the density of the rod, then we can rewrite M as rho A delta X. So Q is equal to C rho A delta X dou U by dou T. Call it as equation number 2. Equating 1 and 2, we get C rho A delta X dou U by dou T equal to Ka dou U by dou X X plus delta X minus dou U by dou X at the point X. Rewriting the equation, we get rho C dou U by dou T equal to K into dou U by dou X at the point X plus delta X minus dou U by dou X at the point X divided by delta X. Now this particular equation represents a differential equation which is satisfied by the temperature function for the portion PQ. In order to get U of xt at a given point, we now take delta x tends to 0. Taking delta x tends to 0 and using the equation f dash of x is equal to limit delta x tends to 0 f of x plus delta x minus f of x divided by delta x. Right hand side of the equation will give us the second derivative of u with respect to x. So dou u by dou t equal to k by rho c dou square u by dou x square. Putting c square equal to k by rho c, we get dou u by dou t equal to c square into dou square u by dou x square, where c square is called diffusivity of the material. This equation, this partial differential equation is called a one-dimensional heat transfer equation.